Okay, so if rho is 5, and remember rho is the radius of in spherical coordinates, then this would have to be a sphere, obviously, with a radius of 5, centered at the origin. And then let's look at phi, or phi. This one, I think once you get more comfortable with spherical coordinates, will be more obvious. Where does phi start? Zero for what? Z. So it's going to be positive z-axis. So it's like 0 phi is up at the positive z-axis. And then it has rotated down pi over 3. And it's all the points where it's rotated down pi over 3. So it could have also gone this way. And it can come forward, etc. So what shape do you think I'm trying to draw here? So I think someone said it. What did you say? Huh? A wedge is not a shape.
A wedge of cheese. That's a shape.
No, it's also coming like this way, that way. Yes, a cone. Then this one, theta is 2 pi over 3. Where does theta start rotating from? It's the same place it's always rotated from since pre-calc. Chloe's the only one who knows.
Did I say it right?
I don't know what you said. The positive x-axis? So if we rotate starting from the positive x-axis, and here's the positive y-axis, then we're going to rotate around till we get to like about here, because 2 pi over 3 is in quadrant 2. But it also could have a negative radius and go into quadrant 4. And it doesn't say anything about rho or phi or anything. So then we're just assuming that it's extending in all directions along this line where theta is equal to pi over, 2 pi over 3. Come on. So this is a plane. And rho sine phi, you might need to flip back in your notes to see what rho sine phi is equal to. What is rho sine phi? The same as r. So this is at r equals 2. So if we're at r equals 2, every point where the radius is 2, bless you. If we're talking about r and not rho, then we are in spherical, where the radius is 2. Everywhere where the radius is 2 is making a circle just on the xy plane. We don't know what z is, so we're assuming it also could be a circle up couple. What shape am I trying to draw, but kind of failing to draw? Cylinder. So this is just to help if there's any questions about like the shape or what help you visualize, etc. Let's actually do some calculus. So just like most other things when you've been dealing with integration, like in Calc AB, you were doing the rectangles, and then we learned in Polar, that's more like a web that you're dealing with, and now we're into three-dimensional shape. So it's like, to steal Chloe's words, like this wedge.
See your shape?
This little hunk of cheese here that we got going on. Now, in our beautiful hunk of cheese, the font is a little crazy on this. This says rho change in phi. That's talking about like this part right here. And then we got this part here is our change in rho. And this last piece is kind of like r d theta, like in Polar. And then r d theta is rho sine phi change in theta. So to go from x, y, z, so like dv and x would be dx, dy, dz, in spherical, you'd have your rho sine phi, and you'd have another rho from right here. So you'd have rho squared sine phi. Change in rho, change in phi, change in theta. This is like the r dr d theta in Polar. This is kind of like the same thing that you have to multiply by. And today we're going to learn more about Jacobians, which are making these little multipliers happen, and like why it's always the same for changing in Polar versus in spherical. Do your army alpha theta friends have a little trauma from using the word Jacobian and none of the lower math people?
Jennifer and will not sound it out.
I would spell it like the base
Jacob,
Jacobi,
I,
Bethea.
So, anywhoozles, in, oops, I have cylindrical, bad copy paste job here by me. Spherical, the everywhere is rho, theta, phi, and just the things to pay attention to. Make sure when you change x's and y's, the x is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. And then dv is going to have to make sure you multiply by rho squared sine phi. This, if there's something you're going to forget to do, I don't think you're going to forget to change the x's, y's, and z's. You're going to forget to multiply by rho squared sine phi. Okay, so we're doing the upper half of a sphere, a hemisphere, if you will. Not quite spherical looking there, but that's okay. What do you think rho is going to be between? Make sure you realize it's on the XY plane is kind of like the easy place to start. So what would rho be between 0 and 1? What's theta going to be between 0 and 2 pi? It has to go all the way around the circle. And then phi, we're starting in the positive z. So that's 0. And then dropping halfway through. So how far did I go until I get to the XY plane? Pi over 2. Phi is only ever going to be between 0 and pi. It's going from North Pole to South Pole. So in this case, we went from the North Pole, NP, to pi over 2, which was like the equator. Okay, so let's transform this triple integral of 16z dv. We're going to go 0 to 2 pi, 0 to pi over 2, 0 to 1. What was z equal to? Huh? Rho cosine phi. And then we're replacing dv with rho squared sine phi, and then do the order that you wrote them in. So if I wanted to get ready to integrate this, could I use the product rule? Look at the boundaries. Are any of the boundaries variables? No. Are any of the functions like adding or subtracting between like rho plus rho squared sine? They're not like adding with each other, right? So because everything is multiplying, we can actually use the product rule finally. Let's rearrange just before we, cubed. And I personally would change the sine cosine to the sine double angle. So we can use the product rule, changing this as sine double angle. Then that means this would be 8. Because remember, 1/2 sine 2 phi is going to be equal to cosine phi sine phi. So that's why I'm halving the 16. All right, 0 to pi is d theta. There's no thetas. 0 to pi over 2 is for my sine 2 phi d phi. And then 0 to 1 is for rho cubed d rho. Okay, try to set up, but do not evaluate for 6. I didn't think it was super ugly. If you need, you're allowed to use your calculator. I don't think you need a calculator. It's just like fractions you might have to add and subtract.
It's like I haven't done fractions since 5th grade.
Which is why you're allowed to use your calculator. Oops. It's between the spheres, but in the cone. Above the cone. Kind of like here-ish. Oh no, between the spheres. My visual's not really working for me right now. So we're between the spheres. We got 2 and 4. Going all the way around the circle, trying to make that. I was trying to make it look 3-dimensional, but I feel like that's making it worse. Theta is between 0 and 2 pi. And then phi is between, since it's above, it's like, whoa, it's starting up here. Oh my gosh, I don't even know what's happening right now. Okay. Starting up here and going down to the cone. So it's not like below the cone's like down here. But above the cone is like, kind of like inside of the cone. Everywhere inside of this cone is above it. It's just not like underneath the cone. So, like, we're really like here-ish in the back dimension and like here on the inside dimension. What? Because I was doing the top part of the cone. Yep. If the shape is one that's like a opening up shape, like the bowl kind of thing also, if it's like above it, then it's like, that's above it. Below is like, if I have a bowl, underneath it is all, like the table is underneath the bowl. Above it is like all the stuff that's still like inside of it, but like up here. I think another way that above the cone makes sense is like, where does phi start? It starts at 0, so we're starting from where it's 0 until it's pi over 3, which is like kind of above it, 0 to pi over 3. Okay, plugging in. We got X, Y, Z, dV. So all of them are going to be multiplied by rho. 2 of them are multiplied by sine phi. And then one's 1 cosine theta, sine theta. And then the Z is equal to rho cosine phi. And then dV, I mean. Let's skip 7 and go to 8. Seven kind of got stuck on this page anyways. Before I forget, could you use product rule here? Yes. So if I asked you to integrate all the way, you would use product rule. You don't have to, but you could. They're all just like multiplying each other, no adding, nothing like no variables in the boundaries. It just makes it, I don't know, it makes it a little less tedious, in my opinion. Okay, and here's, I think, to me, this is not, I never know why people struggle with this, but you do. So, these, you just have to like first write down how the boundaries look originally. So whose boundaries are the innermost integral? Z's. Okay, so it's top boundary, square root of 18 minus x squared minus y squared. Bottom boundary, x squared plus y squared. All right, the middle integral, whose boundaries is that? X. And then the outer one is y. In your work, I should see this written out. This part's the domain. And then the entire thing here is everywhere. How can I determine that that purple part was the domain? Jocelyn? Exactly. So there's only one variable that x is depending on versus z is depending on 2 variables, and y is a constant. So where the constant and the like one variable equals something in terms of one variable is the domain. So let's first graph the domain. All right, we're sketching in the xy. What shape is happening for x? X equals square root of 9 minus y squared. A semicircle. It's a semicircle in what 2 quadrants? Huh? 1 and 4, because that's where the x's are positive. All right, our domain, and then our y's are 0 to 3. Which variable is rotating in the xy plane? Theta, rho, or phi? Theta. But what angles does that mean theta is between? Yes, 0 and pi over 2. Okay, then we have to figure out what's happening in 3D. If I squared both sides of this, I'd have x squared plus y squared is equal to z squared. What shape is that? Starts with a C. A cone. So this part is a cone. The upper half of a cone. And then, oops, I forgot to add dimension here. Upper half of cones, we got this. Opening towards Z. Okay, square everything over here. If you added them to both sides, you'd have x squared plus y squared plus z squared is equal to 18. What shape is that? A sphere. This is the upper part of a sphere. It's really a hemisphere, and it's like the top part of a sphere, the hemisphere. She's talking to me? Huh? Okay.
Do they call it hemispheres like a globe because it's a hemisphere?
Yeah. The more you know. Okay, so it's underneath, it's contained inside the sphere, and its lower boundary is the cone. So it's like an ice cream cone wherever they're meeting each other. So sphere is like the top part of the ice cream, or snow cone might be a better visual. Okay, so we can figure out what rho is between. This would be the smallest value of rho down here. This would be the biggest value of rho, where it's a point basically connecting between the origin and any point on that sphere. So the largest value of rho would be the radius of that sphere. So the sphere, solve so it looks more like a sphere. I don't know why I put Z first. This is what rho squared is equal to. So then rho is equal to only the positive square roots here. I'm like rationalizing the radical to help us solve for phi. So I'm rationalizing for a reason. Rho is between 0 and 3 square root 2. Okay, so phi is definitely going to be something that starts at 0. Its smallest value is definitely going to be 0 for phi. And then we have to figure out how far down we had to go until it hit that point where the cone is intersecting the sphere. We have to figure out how far phi, this is the hardest part of this question, is how far did phi have to rotate till it hit that cone? So finding phi is where did the cone intersect this sphere? They both are equal to z, so let's put them in their z equals format. And then, like, get rid of the square root, so square both sides. All right, I'm moving them all to the same, so the variables all the same side. Reducing by 2. All right, in this situation, if I have an x squared plus y squared, all of these were equal to z. So then just a square root of x squared plus y squared was equal to z. Then what do you think no square rooted x squared plus y squared would be equal to? Yes, z squared. So then z is 3. But we're not in x, y's, and z. We don't want to be in x, y's, and z's. We want to be in spherical. So in spherical, what does z equal? Rho cosine phi. And the reason I wanted to rationalize rho was for right now. So rho is 3 square root 2. This is, I think, going from rearranging the coordinates from x, y's, and z's to spherical. If your boundaries are not constants, this is like the hardest ones to do. Cylindrical is not bad, but going into spherical is kind of tricky. So we're still trying to solve for cosine. Divide by 3, square root 2. We have 1 over the square root 2. Square root 2 over 2. So what would phi have to be between? And remember, phi has to be between 0 and pi. So what does phi actually equal here? Pi over 4. So then our phi's are going to be smallest phi is 0. Biggest is pi over 4. Okay, so then going, that means we have to go 0 pi over 4, 0 pi over 2, 0, 3 square root of 2, and we got x squared, y squared, z squared, so each of them are going to have a row, squared. 2 of them have a sine phi. Oh, and then that's getting squared. And cosine theta, sine theta, cosine phi squared. And then rho squared sine phi. D rho d theta phi. Phi. That might make more sense. Wow, that was so exciting. Man, my page all got off by one here, huh? That's disappointing. You hate to see it. Questions on spherical coordinates? Before we do 16.7, I noticed yet again that I still had the wrong things on the calendar, like for the quizzes. So let's just make sure your calendars are making sense to you. So next class, we're gonna have a quiz on spherical and cylindrical coordinates. I had like the wrong title of that quiz. So that will be spherical and cylindrical. And then we need to BYOP, bring your own pumpkin. And then we're gonna do line integrals. And we're gonna have a quiz on what we'll talk about next. We're doing 16.8 today a little bit, and then also we'll probably need more time to do it next class too. Yep. I don't know about any official days of senior skipping, so I will not change my calendar for that. Good thing I don't have a quiz that day, right? Oh wait, this day? Is this a day? Why? I thought you said it was the 4-day weekendy thing. Well, we'll see what you guys decide. All right, let's do some transformations. So transformations, this is 16.7, it's just like on the wrong page. So changing variables, sometimes changing variables converts a messy region into an easier one. So just like what we were looking at a second ago, like if we were trying to actually deal with these, like those boundaries, it was not gonna be that easy to put those in and simplify and deal with all of that. Especially because when you integrate like z, then it's going to be 1/3 z cubed, and then you have a square root in there. The square root and the square are not, the cube and the square root are not canceling each other out. So it just becomes kind of a mess. So we want to be able to change variables. That's what we've been doing with spherical and cylindrical. We have been changing variables and changing between coordinate planes. We just want to be able to do it if it's not like obviously needing to go into polar or spherical or cylindrical, and instead it's some other thing that would make the transformation easier. So we know polar, like x is r cosine theta, and we know that like dA is r dr d theta, etc. Spherical, we just learned r dv rho squared sine phi d rho d theta d phi. So we might have some regions with known rules or definitions, like what we have been doing. And in those situations, it's easy to find the new limits because you're familiar with those coordinate systems. Sometimes, though, you might need to change from x, y coordinates to like u and v coordinates. That's what integration by parts is also trying to like get you to learn about, is to deal with something that was kind of harder to like put it into an easier formula for you. Let's look at example 1, the new region obtained by the transformation. So if our region R is x squared plus y squared over 36 equals 1, what shape is R? An ellipse. So R was an ellipse, it's a vertical ellipse. whose major axis is 6 in the y direction, minor axis 1. And we want to do a transformation. So here's our transformation. We want to transform x to equal u over 2 and y to equal 3v. So doing this transformation, substitute what x is equal to into the region and what y is equal to. So we get u over 2 squared, which becomes u squared over 4. And we have 9v squared over 36. What is 9 over 36 reduced to? 1 over 4. So we could multiply everything by 4. And what shape did it actually become? A circle. It's a lot easier to deal with a circle whose radius is 2. Because now we can just apply polar rules. You're like 0 to 2 pi, r is between 0 and 2, etc. So we have been doing a Jacobian. I just didn't feel like having you calculate a Jacobian every single time you wanted to integrate something from rectangular into spherical, but you could do Jacobians for each one of these. So a Jacobian matrix is doing a transformation where x is equal to a function of u and v, and y is equal to a different function of u and v. So we have it's a matrix of partial derivatives. It's the Jacobian matrix. So we're taking the derivatives of x's and y's with respect to u's and v's. Basically, the derivatives of x are going to be the first row, and the derivatives of y are going to be the second row. And then with respect to u is going to be the first column. And with taking the derivative with respect to v is going to be the second column. So this is going to be del x, del u, del x, del v. Whenever you input into a matrix, you really want to get in the habit of inputting rows and then columns. So that's why I did my derivative this way. So we're inputting into this as a row, and then the Roman column stood up. Now I'm going to the second column, or second row, first column. And the Jacobian matrix is also telling you to do the determinant. That's why it has the vertical bars. If it was just a matrix, it would have the braces, so it would have like edges on it. But just having the absolute value bars around the outside is telling you to do the determinant. So remember, if you want to do a determinant, of a 2x2 matrix, you're going to do A times D minus the diagonal going up So if we're doing double integrals, we're integrating a function of x and y over the region R. But R has transformed into S, which may be like R was that ellipse and S is the circle. You have to have change everything, all the x's and y's, to now be functions of u's and v's, but you also have to multiply by that Jacobian matrix. So if we had some region, R, that we were integrating a function of x and y over in dA. Now we're going to have a double integral over new region S that had the transformations applied to it. We're not just like making it up. We have some legit transformation happening. And then plug in to the function whatever x was equal to in terms of u's and v's, and whatever y was equal to in terms of u's and v's. And then we have to multiply by the Jacobian matrix to finish the transformation. This is helping us go from rectangular to polar, or rectangular to spherical. That the r d theta is the thing that we've been multiplying by. That's because that helps us change coordinate systems. So it's like part of the dA. So just to prove to you about a polar transformation. X is a function of r and theta. And we know already that to do this transformation, we would have r cosine theta. And then y is some other function of r and theta. And we know that function to be r sine theta. So doing the Jacobian, let's set it up. So first I'm taking the derivatives of x. First, I'll take the derivative with respect to r, and then with respect to theta, and then y. Okay, derivative of x, r cosine theta with respect to r. What do we have? Kai. Derivative of r cosine theta with respect to r. I think you just integrated it.
Oh.
Derivative. Okay. And then what's the derivative of x with respect to theta, Chance? I can't hear you. R over theta squared? Oh, but derivative of cosine's not positive. Negative. All right. Gary, derivative of y with respect to r. That was too easy. Carly, derivative of y with respect to theta. R cosine theta. All right, now we're going to find the determinant. All right, so we got r cosine times cosine minus negative r sine times sine. What could I factor out from both of these terms? An r. And then I have cosine squared theta plus sine squared theta. Oh my gosh, what does that equal? 1 times r. It's almost like why we've been multiplying by r dr d theta is because this was like the Jacobian multiplier thing. We just didn't want to do that every single time that we had to do that transformation because it happened so much. Now let's kind of maybe set up for the transformation. So if we're going in 3 dimensions, same kind of deal, but instead of having a 2 by 2, what kind of Jacobian do you think you're going to have? A 3 by 3. Before I forget, this is the polar. So if I wanted to apply it to spherical, x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And the more you write these, the more likely you are to not forget this transformation when it comes to the quizzes and stuff. I should add these as a flashcard. Doing our Jacobian. Probably feeling a little too lazy to do the full Jacobian out. Oh my gosh, it happened here too. That's so disappointing. My mess up. Okay, so we're gonna have x's, y's, then z's be the respective rows. And please know that this is like not, you don't actually label the things like how I'm labeling it. I'm just doing it so that you can kind of like follow along what I'm doing later on, but you don't put these like variables there. Like if you like looked in a book or something, it's not going to have x, y, and z. You just kind of have to like interpret it. And then this is going to be with respect to rho, with respect to theta. Okay, so what's the derivative of x with respect to rho? Yeah, cosine theta. Yep. And then y would be sine. And z would be cosine. I think you know what? Let me let you fill the rest of these in. A fun experience for the reader. That's what my calculus books used to say. This is left as an exercise for the reader. Oh, thanks. Great. So helpful. Chloe, what's the derivative of x with respect to theta? Good. All right, and then we're going to have positive rho sine phi cosine theta. And then what's the derivative of z with respect to theta? 0. All right, and then with respect to phi, Karen, what do you think? Rho cosine phi cosine theta. Good. Then we are going to have rho cosine phi sine theta. And then hopefully, ooh, wow, that row is really cute. Rho sine, ooh, negative. And then how would you find the determinant of this? Trash can method. And then you would cry a little bit because this would be taking you 10,000 years. And what do you think this eventually will simplify to be? Rho squared sine phi. Yippee! So instead of doing all of that, we just like memorize it. If you don't want to memorize it, feel free to do all of that other fun stuff. Godspeed to you. That's not my choice. That's your choice. Yeah. Oh yeah. We should go to the boards and.
That's not what I said.
All right, let's try to do one of these transformations. There's kind of two main ways that you're going to see the questions asked. Sometimes I'll also give you points on a parallelogram, which we'll probably practice next class a little bit. But the two main ways is telling you exactly what x should be in terms of u and v and y, etc., or giving you like lines. And you're trying to transform those lines. So these are kind of like the two-ish main ways. Here's our original region. And we're trying to do a transformation to get to, this is the transformation that we have, to make this easier to deal with. So right now, we don't really know how to integrate with, this is an ellipse. I don't know if you can tell. Originally, the region's an ellipse. We want to do a transformation to try to make this not be an ellipse anymore. So going from transformation 1, I wonder if I can fit this in this page. I probably have enough room to go to the next page. Okay, so doing transformation number 1. Going from the ellipse, what do you think I'm trying to transform this to? A circle. I need the Jacobian. So we're talking about doing the Jacobian, like we're using the transformation to do the Jacobian. Jacobian, nope. I'm stupid. Okay, so x with respect to u, what is that going to be? 2. X with respect to v, 0. Y with respect to u, 0. Y with respect to v, 3. And do your determinant. What's it equal? 6. So this is when we do transformation number 1. dA is going to become 6 du dv. All right, we're trying to integrate this elliptical region. We just took the region from being, we got to also figure out from elliptical into circular, how it will transform. So the 6 is just the multiplier in the area. Plug in x is 2u, 3v. I think we can do that math. 36u squared plus 36v squared is equal to 36. All right, we were within the region. We were the region bounded by this ellipse. So it really was like the region inside this ellipse, 9x squared plus 4y squared less than or equal to 36. Then we're doing a transformation to get it to be u squared plus v squared is equal to 1. Why it's less than or equal to is because it was bounded by. So this means like that's like it's within that ellipse. Okay, so we have a second transformation. You might not realize initially, but like what, I don't know, some of you might. What transformation do you think I'm going to go into when I've now changed this into a circle? Polar. Me making it into a circle was one of the transformations. Going from an ellipse into a circle was transformative. Now we want to make that not have to be like v is equal to the square root of 1 minus u squared as like the top part of the circle. We want it to be in polar. So transformation number 2. Maybe I don't have enough room. Transformation. Going from u's and v's into polar. R's and thetas. So we'll let u equal r cosine theta because it seems like that's kind of the first thing in the alphabet, like how x usually is. And then v is r sine theta. We're going all the way around the circle, so theta is between 0 and 2 pi. And our radius was 1, so we're between 0 and 1. What do you think the Jacobian for du, dv, del r, del theta is going to equal without having to do it? R. If you want to do it, feel free. Oops, this is a 0. So for transformation number 2, dA is going to have r and then be dr, d theta. Questions on anything we've done thus far? All right, our original thing was double integral over that region that was an ellipse, x squared dA. Then we did transformation number 1. And our region became u squared plus v squared is less than or equal to 1, a circle. And what was x equal to? 2u, so in it, 2u squared is what x squared became. And dA became 6 du dv. Then we go into polar. So transformation number 2. 0 to 2 pi became our region. 0 to 1. So really now we have 2 r cosine theta squared times 6 from the previous region. That's still there. And that's also the 2 is from the previous region as well. Because it was 2u. But then u was equal to r cosine. 6 was from the previous thing. And then we have dr, d theta. Thank you. Now this is actually pretty easy to integrate. You're just integrating r cubed. 0 to 2 pi cosine squared theta. Ooh, gotta use an identity. And then 0 to 1. Got 4 times 6, 24. R cubed. dr. If we had more room. Maybe you have more room. Maybe you didn't write as big as me. I think you could integrate this pretty easily. Let's remember how to integrate. What do we have to change? I'm going to call him Ben because he's in BC as well. Ben, cosine squared. What am I changing that to?
That could be 1/2 all times cosine 2 theta minus 1. 1 cosine 2 theta plus 1.
Yes. And do a little magic and you get 6 pi. Yay. Made that look like it was coming from the cosine 2, but equals, dot, 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 equals. This is an adventure for the reader. All right, let's try to do example 3. I like these straightforward ones, but they're kind of like, I don't know. To me, this is like not that climactic. Like it's a little like we've been doing polar. Like this isn't all that exciting. I think example 3 is more of the level that I would like you to operate at. So let's graph the little parallelogram that we're enclosing in. Where are you going, Ben?
I have to actually finish an essay. So
Huh? My parallelogram wants out?
He wants out because he heard
that's true.
Ben, don't say things like that. These are parallel, in case you didn't pick up what was going on, since it's a parallelogram. You know what I'm saying? I'm trying to draw them more parallel with each other. X-intercept's at 4. Okay, then this one. Y-intercept is at -1. You're welcome. Well, I went a little too far down on that one, huh? Okay, then this one, y-intercept at -8. That's way too far away for me to draw. Okay, over here, make it look like a parallelogram. Scooch it a little closer together. Wow, what a beautiful region. I worked so hard to make that look so accurate. Hang on. They're not quite intersecting. Okay. So this is the region we're enclosed in. Dealing with parallelograms, while you could, right, we could do like the cross product between them or whatever, find the area of it. Instead, we could just do a transformation. What do you notice is happening? Like, specifically before the constants. Aren't those kind of equal to the same things? And these two are equal to the same two things? So let's just oh, and then look at what we're integrating. Wait a second. Oh my. So let's let a variable equal x minus 2y and a different variable equal 3x minus y. So I'll just make u be x minus 2y and then v be 3x minus y. So then what would u be between? Zero and 4. And then v would be 1 and 8. You guys get where I'm getting those numbers from? Like what each of those equations is equal to? So our new region, let's graph these. We're going to treat u like it's the x variable and v like it's y. So at u equals 4, we have a vertical line at 4. And 0. And then v equals 1. Obviously not to scale, but you know, you get the gist. What shape do we have now? A rectangle. Wow. Let's do our Jacobian. We were in x's and y's. But we want to actually figure out let's set up our matrix here. We've got x's and y's. What do you foresee being an issue? Because this is different than what we've had before. Right now we have x equals in terms of, u equals in terms of x and y. Before, when we've done all these transformations, like up here, we had x equals in terms of u's and v's. So we had like our little numerator, the space we were going from is in the numerator, and what we want to go to is in the denominator. But right now, and it's always been like the dependent variables equals independent variables. Right now we have the ones we're trying to transform to equals in terms of the ones we were trying to ones we were trying to transform into equals the one we were trying to transform from, which is weird. So fun fact, that transformation that we have to multiply by is equal to 1 over, and it always works, the Jacobian when we flip them around, like the reciprocal. So before I had, I think it was Tommy Cherry back at Suncoast who discovered this rule was true and proved it to me. Before we discovered this, we used to have to do a whole system of equations to figure out how to solve u and v's to be x equals and y equals equations, and it was really tedious and terrible. So instead, we just do the reciprocal. So let's do du v x. Because this is easy to deal with. I know what u is equal to. What's the derivative of u with respect to x? U respect to x, 1. What's the derivative of u respect to y? Negative 2, 4. Huh? Highlight this one, highlight the other. Okay, then v with respect to x, 3, and then negative 1. All right, multiply on the diagonal. 1 times negative 1 is negative 1 minus 3 times negative 2 become plus. So my transformed area is going to be 1 over 5 du dv. You have to flip it. Don't forget the flip. We're not multiplying by 5, we're multiplying by 1 over 5. All right, and then our region was x minus 2y over 3x minus y dA. Now it's going to be 0 to 4, 1 to 8, u over v times 1 over 5 dv du. All right, integrate this. I believe in you. Can you use the product rule? Yes. What's ln of 1? 0. So we should be able to simplify this fraction Chloe, what does this simplify to be? 16 over 10. What is that simplified?
The first student divided by 6 over 5, and you're done.
Wow. What a difficult thing you just did.
That'd be step by step.
Okay, yippee, we did it. That's the end of chapter 16. I'm so disappointed that now every single page is like up on the next page. Is that going to be like the whole? Yep. Awesome. That's so great. Okay, cool. Oh, okay. I didn't screw it up after there. So 17.2 starts to be better.